Hello and welcome to this module on Introduction to Online Learning. So, where we will look at the basics of one form of reinforcement learning. So far, we have analyzed data to derive insights, but we never actually looked at the question of how do we obtain the data until the last couple of modules, right? We already saw designed experiments, we also looked at active learning, but what if there is a cost associated with the data? And what if the outcome is stochastic? So we try to make measurements about the data. So we want to make a prediction about what will happen if a patient is given a certain medicine, right? But the patient is sometimes cured, sometimes is not cured. So there is some amount of stochasticity about the outcome of this experiments or this data measurement that we are trying to do. Right? So when are we sure we know the outcome sufficiently well for us to treat it as a proper data point? And when are we sure we know the best possible choice given the circumstances? Suppose there are multiple recommendations that you can give to a patient, and each of these could have a uncertain outcome. So how are you sure? A, what is the outcome? B, which among the outcomes is the correct one? Correct. So how do we go about answering this question? So these come up in a variety of settings. I was just talking to you about the drug and to treat a disease. You could think of more mundane things like what is the right advertisement to show to a user who comes to your web page, right? Or what is the right scheme or insurance scheme to sell to a customer whom you are trying to canvas, right? Or if you're playing a game, what is the right move to make in a game, right? Or what's the right movie to recommend to a person? So there are many different situations where we have similar situations arising. So these kinds of problems are sometimes called stochastic multiple choice problems, and are frequently modeled by what are known as multi-arm bandits. So people might have heard of slot machines, which are gambling machines, where you put a coin in and you pull the lever, right? And then if all the three pictures on the machine turn out to be the same, you get some kind of a payoff. So you get a lot of coins back, right? So in a multi-arm case, you don't have a single arm to pull, a single lever to pull. You have multiple levers, and each lever has a different chance of success. And you have to pull each of those levers often enough to understand which of those levers is the best one to pull. So it's very similar to the kind of scenario that we have been talking about so far, right? So little formally, so the n-arm bandit problem, right, is to learn to preferentially select a particular action or an arm from a set of n actions which we will conveniently label 1 to n. So each selection results in some kind of an outcome which we will call as a reward derived from a probability distribution associated with the respective arm, right? So arm could be a medicine that you give to a patient, and the reward could be whether the patient survives or not, and the probability of survival of the patient is determined by the system, right? So what disease the patient is suffering, what are the other conditions that are prevalent at the time, and what is the efficacy of a medicine, and so on and so forth. Variety of factors determine what is the probability with which the patient will recover, right? And so the assumption is that each arm I is going to have a reward that is distributed with the mean mu I as one best arm, and the payoff or the reward for that arm will denote by mu star, which is the max over I of all the mu i's. Okay, this is the basic problem description. So you can look at a few examples of problems where this is used. Here is Yahoo News front page from some time ago, and so they have the editors at Yahoo News select a few tens of stories among which the front page news items are selected, and then you could think of a reinforcement learning algorithm or a bandit like problem where you're trying to maximize the reward. In the case of this kind of news story customization, it's going to be how many times did the user click on a news story. So I have something like 20 stories to choose from. I choose one story to make my lead story, right? And the payoff or the reward that I'm going to get is how many times people clicked on the lead story. Okay, so this is like a bandit problem. So now the question is, unless I show something as the lead story, I'm not going to know if a person is going to click on it or not, right? So how many times should I show a news item as a lead story till I know what is the probability of a person clicking on the lead story, right? And how sure can I be that this is the best news story and that I don't have to show anything else to the user, because I know what is the right estimate for the clicks for all the other stories. So this basic problem is called as the dilemma between exploration and exploitation. We really want to explore to find a truly profitable action. We don't want to just stick with the first story that we show to the user. We really want to explore to figure out which of the stories is the best story. But at the same time, we would also like to exploit whatever knowledge we have so that we can get a lot of reward. So we can get more click-throughs. So when do we stop exploring and start exploiting? So bandit problems, in some sense, encapsulate this explore versus exploit dilemma and give us different approaches for solving this. Right? Here are a few more examples. So somebody types in a query, hotels in some place, and then the search engines are going to throw up a lot of ads. In fact, people use the similar algorithms to the bandit algorithms to decide which are the ads that need to be shown on a web page. So again, as you can see that each of these ad is like an arm on the bandit problem, and if you click on the ad, you get a payoff. And you could also think about recommendation engine. So if people would have seen this on Amazon or in other places where people who like this also like this, or people who bought this also bought this. So these kinds of recommendations, right? So you could think of these recommendations also as bandit problems. So if you show a recommendation to a user and if the user clicks on it, and then you get a reward. But really, just hold on a minute. Is it really a bandit problem? You know, people typically think about customers who bought this, also bought this, customers who bought items in your recent history also bought. So you could think of variety of different rules that allow you to make these kinds of recommendation. Right? But if you stop and think about it, these rules actually could give you many choices, and which among those choices are you going to show to this particular user who has come to your web page right now. So that can be treated as a bandit problem, and people have tried to look at it in that fashion, right? Here is the last example that we look at. It's on comment recommendation. So if you think about many blogs, people are pretty active in commenting on the main news story, and when a user comes to the blog page, you would really like to show the user the comments on the story that are most relevant to the user, right? And so once you show a comment, if the user could give a thumbs up or a thumbs down, and depending on the reaction of the user, you know whether it was a good action to take or not, and these thumbs up and thumbs down serve as your rewards, right? Just to recapitulate, so the main problem description is that you have n possible actions, and the learner has to preferentially select a particular action so as to get as much reward as possible. So each selection results in some rewards derived from the probability distribution that is unknown to us at upfront, right? And making a simplifying assumption that each arm I has a reward distribution with mean mu I, and that is one arm that gives us a mean reward of mu star, which is the maximum over all mu. So I'll stop here now and then I'll continue in the next module.